Hello, my name is Donghyun Gu, and today I'm going to review the paper Patfig Generating Short and Long Captions for Patent Figures. Contents are followed. Patents serve as a core institutional mechanism for technological innovations at the strategic intersections of AI and IP. Patent figures a central role in understanding patent applicants and explaining inventions. Patent figures consist of various of visual forms, including technical drawings, block diagrams, flowcharts, or etc. Understanding patent figures requires the joint considerations of visual informations and accompanying textual descriptions. Such vision language alignment supports a range of downstream tasks, including image-to-text generations, figure-based patent retrieval. Enhancing the connection between visual representations and linguistic descriptions is essential for comprehending complex and abstract technical content conveyed through the patent figures. The object of this paper is bridge visions and language for patent figures by developing a patent-specific figure compositioning framework using the patent dataset. The theoretical contribution is that extends vision language research to the patents domain and highlights the importance of visual representations in facilitating human cognitions of abstract and technical concepts within patent documentations. The practical contributions is that providing practical supports for patents attorney and practitioners by improving the quality and clarity of patent figure captions. Also contributes resources that can facilitate more efficient and accurate preparations. Existing patent figure datasets have primarily been constructed for image-based patents retrieval tasks. The dataset provides two related datasets. It consists of only 211 patents and employs coarse image classifications across 9 categories. But Patfig is a comprehensive dataset comprising 30,000 patent figures extracted from more than 11,000 patents. Each figure is richly annotated with short and long descriptions, figure types, and references numeral with corresponding terms. However, extracting such descriptions from patent documents remain challenging due to the diverse caption structures and interpret placements of reference numerals within the texts. Prior research has primarily focused on figure-based patent covering and figure classifications. While these studies contribute to the retrieval and categorizations of patent figures, they do not address natural language descriptions generations for patent figures. For scientific figure captioning, which employs LSTM-based models with attention mechanisms, with recent advantage in large visual language models, extensive research has focused on effectively aligning visual features with the texture spaces. Representative LLM models such as Llama GPT-3 have been extended to LVLMs and have demonstrated strong performance across various visual language tasks. However, the applications of these models to patent figure captioning remaining insufficiently explored. Patents database contains complete patent texture data from EPO, including publication number, title, abstract claims, IPC codes, inventors, and etc. This database serves as a foundational resources for accurately linking patent figures with their corresponding texture informations. Based on the texture database, patent publications number within the period from January 1, 2020 to December 31, 2020 were selected. A total of 62,513 patent images were acquired from 15,645 unique patents. By matching images to patents using publication numbers, a reliable image-text linkage was established. Short descriptions of patent figures generally follow a standardized format and separated by line break. These descriptions are typically located in the brief descriptions of drawing sections. Typically short captions beginning with a figure number followed by a brief explanations. Due to this structure's consistency, a rule-based automatic extraction approach can be effectively applied. The extracted results are organized into structured sentences that include the figure number, reference objects, and viewpoint informations. Long captions are distributed throughout the patent specifications and exhibit diverse paragraph structures. To address this issue, text normalization is performed, followed by searching for repeated references to figure numbers. Descriptions relevant to a given figure are restricted until the beginning of another paragraph or the appearance of a different figure reference. Long, overly verbose descriptions are trimmed during post-processing. Figure types are extracted by leveraging the common sentence structures observed in short captions. A rule-based restrictions method is applied to phrases that appear after key expressions, such as are, is, on, shows, illustrate, and depicts. Through this process, an initial set of 1,506 distinct figure type classes is obtained. The extracted figure type classes are refined through manual revisions and text normalizations. Frequently occurring figure types are then grouped to construct a figure type taxonomy. The taxonomy is organized from less abstract figure types to more abstract figure types. Optical character recognition (OCR) is employed to extract reference numerals appearing in patent figure images. The extracted reference numerals are matched with corresponding figure descriptions and terms to ensure image text consistency. This process enables the explicit alignments between objects depicted in figures and their textual descriptions. To compare information extractions performance on patent figures, 4 OCR libraries are evaluated. For evaluation, 54 patent figure images are randomly selected from 8 IPC sections. Each image is manually labeled with reference numerals and figure numbers. Considering that many patent figures appeared in different orientation, OCR performance is tested by rotating images at 0, 0 degree, 90 degree, 180 degree, and 270 degree. Among the evaluated libraries, DOCS-TR achieves the highest accuracy. In image captioning tasks, CNN-RNN-based models have been widely adopted. However, due to the recurrent natures of RNNs, this model suffers from limitations in feature representation and restricting training parallelization. Given that patent figures are domain-specific and technically complex, CNN-RNN-based approaches alone are insufficient to capture fine-grained semantic relationships and contextual information. Recent trends in vision language tasks have leveraged autoaggressive language models and cross-modal transfer. According to this, studies adopt Mini-GPT-4 as the baseline model for patent figure captions generation. A total of 3 model variants are constructed for performance comparisons, a vision-only model, and 2 variants of vision text models. The quality of generated short and long captions is constantly evaluated, such as BLU, log, material, and CIDER. The Mini-GPT-4 model is fine-tuned separately for short captions and long captions. Both models are trained for 10 epochs. The maximum text length is set to 50 for short captions and 500 for long captions, respectively. Mini-GPT-4 consists of vision encoder composed of a pretend vision transformer and a Q-former. During fine-tuning, only the linear projections layer is trained to align visual features with the model. ManageGPT-4 provides a two-stage pre-training schema. In the first pre-training stages, the model acquires vision's language knowledge from a combined dataset of conceptual captions. In this study, additional training is conducted based on the second stage fine-tuning settings. A vision-only captioning task aims to generate figure descriptions using only an input image and the general prompt. The prompts used in this setting is as follows. Please provide the detailed descriptions of the figure. The input configurations is limited to a single image and a simple texture prompt. The input image is provided to the model and processed based solely on visual information. The model generates captions describing the image without any additional text-based context. The objective of this experiment is to assess the model's image comprehension and descriptive performance under the vision-only configuration. Vision plus text captioning task aims to generate figure descriptions using an input image together with a prompt that includes patent-related texture information. The texture input consists of the patent title and terms corresponding to reference numerals. Two prompt configurations are used. Request figure descriptions associated with the patent title. Request the figure descriptions associated with the patent title and explicitly includes reference numerals and their corresponding terms. This experiment aims to evaluate the impacts of adding text-based cues on captions generation performance. The model uses the figure image as visual input and incorporates the patent title and terms as additional texture context. This setting evaluates whether more specific and conceptually appropriate captions can be generated. The term information is retrieved from the complete descriptions of the patent application. Quantitative comparison is conducted across different input configurations for both short and long captions generations. The results of the various captioning configurations is shows at Table 3. Short captions rely more on concept visual summarizations, and that additional texture information may introduce ambiguity or distraction. The quality examples it shows at Table 4 provide an intuitive comparisons between ground truth captions and generated captions. For long captions, texture cues facilitate more detailed descriptions of components, relationships, and functional roles. Short captions, on the other hand, tend to focus on capturing the overall structures or figure type rather than detailed semantics. Long captions tend to mention the components referred to by the reference numerals in the figures. Accordingly, long captions generation generally benefits from adding terms to the input, leading to overall performance improvement. In contrast, short caption generations tend to be negatively affected when a list of terms is added to the input. When texture cues are added, the model may overlook critical visual features, resulting in less accurate captions. In addition, conflicts between texture and visual cues may confuse the model. For these reasons, model performance is generally better than reference numerals are excluded from the evaluation. The Patfig dataset demonstrates that LLMs can operate effectively even on domain-specific and highly complex visual materials, such as patent figures. Short captions and long captions. The study suggests that LLMs can dynamically integrate visual and linguistic information depending on the type of input required. The proposed future directions of generating figures directly from the patent text holds significant potentials for streamlining the work of patent attorney. Various experimental configurations such as change in training dataset size, prompt design, and the inclusion of texture cues during the fine-tuning stage have not been sufficiently explored. Experiments involving training on text with reference number removed or removing numerical labels directly from images. It remains unclear at what point feature inputs becomes redundant for text generations. That is, when a text-only large language models can accurately predict the context of a figure. Thank you for listening.